Okay, everyone. I am Shiv Prakash, research scholar, Department of Electrical IIT BHU. Today I am taking a class of live session 6 for the assignments, 6 assignment for subject of design of photovoltaic system. The sixth assignment related to the maximum power point tracking from the PV system. It means how you get the maximum power from the PV panel. Here the first question related to the which one of the following is best DC-DC converter for the maximum power point tracking in the PV panel. Someone says C option. Yes, this is correct option. VPV, IPV. This is the solar voltage, solar current. You know about the characteristic. The a point where the maximum power you get. This one is the maximum power point. This is the load line. 1 by R. If you take in this one, RT is the terminal of the panel, solar panel. 1 by RT is the load line of the PV panel, PV system, solar system. To get the maximum point, you should operate to get the maximum power from the solar. You should operate the PV system at this point, like a maximum. There's the VM is the maximum voltage at the maximum power, and this is the current at the maximum power point. So now IMP or IM. To get the maximum power, you should operate the solar system to that point, a to that load line. If you operate this load line, you can definitely get the maximum power. But this is depending on the voltage and current profile. But every load is not exact profile of the this solar system profile, like a voltage, same voltage current and current, because of load is the different type of load or the electrical system. That's why you can't be say that the every load can get the maximum power from the solar. To get the maximum power, you should operate at that region. You should operate at that point. It means if a solar panel specification given is maximum voltage at the maximum power point, uh, point, and the current at the maximum power point. If this load profile is matched from the load to the PV panel, then you get the maximum power. But if you load, it does not match exactly from this. To match this one, we add a system like a converter, DC-DC converter, to match the load to the source, load impedance to the source impedance. Like this one is the PV system. If you connect a direct load from here, if you connect a load here directly, this is the Vt. At that point, you can't be match this one from load to the PV solar profile. So because of the load has a different type of load like a current and voltage. If you I let a load connect with a higher current rating, that's why the voltage will be very reduced, so that it can be get the maximum power. That's why you, at this point we connect a converter like DC-DC converter. After that you connect the load to match this one, to match the profile from bit input to the output. This is the DC-DC converter. Many type of DC-DC converter like isolated and non-isolated. Basic DC-DC converter is the buck converter, boost converter and buck boost converter. This is the basic DC-DC converter. From this one you can make a different type of converter. But a question is asking about the which one is the best for this DC converter. It is depending on the region where you operate the your PV system. Buck converter, boost converter, buck boost converter. These are different type range. This the different operating region. All of them. To choose the best buck converter, you should know about the impedance, input impedance of the converter. If you know about the input impedance of the converter, the input impedance of converter is work as the load of the solar panel. This one. If you find this one are in, sorry, input resistance of the DC converter, it this is the work like a load for the solar PV. This one is the source and this one is the load for the PV. Because of final load is the RL for your side, but for the PV panel or PV source, the whole of the converter and your load is act like a load. That's why you, for the maximum power point, you should match the input impedance to the load impedance. That's why first of all find the input impedance of the any converter. After that, match the profile from the source PV system. After that, you can see which one converter is the best suitable for the maximum power point. Okay, this is given as the boost converter, buck converter, and buck boost converter. Cascade buck converter, it means the two back to back converter, buck converter connected in the series. First of all, find the input impedance of a boost converter. The boost converter connected is a solar PV. Boost converter, you know about the VS input voltage. After that, a inductor. After the switch, so a diode, output capacitor. This is the load. This is a variable load. You have a Yeah, you can say this one fixed load. You can make a variable by the changing the duty cycle. This one same as the IL. IT is same as the IL input current, inductor current, so the I naught. I think we know about the buck converter, boost converter. I can directly here. For the switch is on, means Q is 1. The switch is on, this one is close, and current flow like that. Means the inductor will be charged. Then what is the VL? VL is same as the VT. And this current IC is the minus of I naught, because this current flow is the in opposite direction. This one is the reverse bias. And for the switch off, it means 0. For a 0, this one will be off. Then this current flow like that. By the KVL, VL is equal to VT minus of V naught. Capacitor current, same IL current flow like that. Then IL current minus of I naught output current. I think all of you know about the inductor transformer. Inductor or transformer cannot operate at DC input source. Here the solar system, a solar PV, is give the electric in the DC system. This is the DC current. Then how will you operate the inductor and capacitor in DC system? Because of the inductor and capacitor is not operated in the DC system. Inductor is short circuit and capacitor is open circuit. If you apply as DC at the terminal of the inductor and capacitor, then if you want to work the inductor to work a capacitor, then you should maintain the flux, average flux it be 0. It means which amount of the flux will be charged, then discharge will be the same. If you charge the inductor, like flux will be stored, after that you decrease the discharge the inductor, flux will be decreased, then increase and decreasing flux will be same. It means the volt second balance is saying that the flux balance also. Flux balance, it means the charging and discharging flux will be same. If you charge more, it means flux will be increased and more, charging flux will be more to the discharging flux. At that point, the inductor get the saturated. Same thing in capacitor also. Capacitor is known as the current second balance. It means the capacitor charge of the capacitor should be maintained as a charging and discharging time. That's why the average of the voltage of inductor will be 0, and Same thing for the capacitor. This current, average current of the capacitor will be 0. In any point, if you want to operate in DC system for the inductor and capacitor, then you should maintain that point. Average, it means this one is the DT time, on time. You know about this one, on time. This one will be 1 minus D into T time. So it will be off time. Then average of this one, it means on time and off time. The average of the voltage of capacitor, voltage of the inductor will be 0, and current of the capacitor will be 0. That is first one. Apply a Bolt second balance equation. Bolt second balance it is also known as the flux balance. Flux should be maintained at a point. Should be charge and discharge. Flux will be same. How much you charge, then same flux should discharge also. Sorry. Bit into time. Time is the dt time, on time plus off time on time will plus on off time divided by total time is the average of the inductor voltage is equal to 0 for the inductor. The TT cancel out. This one is the VT. On time voltage is a VL, it means a VT into D plus off time VT minus of V naught into 1 minus D is equal to 0. VT into D plus VT minus of V naught minus of D into VT plus of D into V naught. D into VT is cancel out. You common of V naught, then you get in this one minus V naught, then you get 1 minus D, and the right side is the minus of VT. If you transfer from left side to right side, then what will the output voltage is VT divided by of 1 minus D. This is the output voltage. Something find the output current equation also with respect to the input current. Apply current second balance or charge balance for the capacitor. Same thing, dt into IC plus of 1 minus dt time off time into IC divided by total time period is equal to 0. D into minus of I naught plus 1 minus D IL minus of I naught minus of D into I naught plus 1 minus D into IL minus of I naught plus of D into I naught is equal to 0. D into I naught will be cancel out. I naught is equal to IL into 1 minus D. For the boost converter, you can see here IL is same as the IT. Then you can replace this one. I naught is equal to IT into 1 minus D. The input current, this one output current. Then you know about the resistance. V naught is equal to I naught. R naught is equal to this one. Then V naught is equal to Vt divided by T of 1 minus D into I naught. I written here I naught. I naught is equal to IT into 1 minus D. It means Vt divided by IT you can written as the RT, or input of the boost converter, input resistance of the boost converter, into 1 divided by of 1 minus D square. Then you will get the RT is equal to R dot into 1 minus D of square. This is the input resistance of the converter. Then input resistance of the converter is the work as the load of the PV system. Then to change this one you can get the maximum power point, because of the two this one can matched exactly from the PV system. You you don't know exactly what the resistance of the input source like PV system. That's why you can change the duty ratio and then match this resistance to the input source. It means to change the load, this one work like a load for the PV, to match the impedance to the source like a PV system to get the maximum power. Then you know about the load line. So in Vt, this one current, maximum power you can get here. So maximum power point line, you can say this one. A load line, this one for the maximum power. This one Vm, this one Im. This is the maximum power. You have RT, you can define 1 by RT for the load matching. T is equal to 1 divided by of R naught 1 minus D square. D should be vary from point 0 to 1 only. At D is equal to 0, 1 by RT is equal to 1 by of R naught, and at D is equal to 1, 1 by RT is equal to infinity. It means this is so as the short circuit. 1 by RT is infinity, it means RT is equal to 0. Unit terminal resistance will be 0, it means short circuit. Then that point, this point you can find here. Okay, this point, it means D is equal to 1. At D is equal to 1, 1 by RT is here, and at D is equal to 0, it will be 1 by or not only. What is the load you connect? It should be here, from here to here, anywhere. It can be anywhere. You don't know, it is depending on the or not value. I written here at d is equal to 0, 1 by RT is equal to 1 by f R naught. It means 1 by RT vary from 1 by RT is varied from here to here only. From d is equal to 0 to d is equal to 1, then this will vary from here to here. In this region, if a maximum power point is available, then you can get the maximum power from the PV. If the maximum power line is not in this region, then you can't be get the maximum power in boost converter system. In boost converter, this is the region to get the maximum power only. D is equal to 0 to 1, you can vary from 0 to 1 only, you can be very beyond this one. In that point, the 1 by R naught is depending on the load resistance. From line here to here, you can vary to get the maximum power from the PV. But if the maximum power point is the in range of this one, then you can get the maximum power. Same thing you can do from the boost buck converter. For the buck converter, I am written directly. You can do the my own all of thing, like you switch it on off, then find the volt second balance, current second balance. You can get the input current equation and voltage equation. Voltage divided by a current is the resistance. Input impedance of the buck converter. Buck converter, you know of the circuit. This is the switch, freewheeling diode. This will be an inductor, the output capacitor and resistance. This is the load or not. This is the VT. This is the IT. Terminal current, terminal voltage. The buck converter, you know about the output voltage is equal to dVs. Here the VT, duty cycle and terminal voltage, input voltage. I naught is same as average of I naught is same as the IL, average of inductor current. IL is here. I'll divide between I naught, I naught and IC. IC is the capacitor current. IL is equal to I naught plus of IC is the capacitor current, but average of the capacitor current will be 0 by the current second balance equation. Average of the voltage of average voltage of inductor will be 0 and average current of capacitor will be 0. That's why if taking an average of this one, for the average value I will write in capital letter. This will be 0. That's why IL is equal to I naught. But we have required for the input current. For the input current, looks, see here, this one on time, this one off time, and this one on time. Inductor current, inductor voltage, inductor current, and this one is the input current or IT. The switch is on, then if the switch is on, then Vt minus of V naught appears on the inductor. This will be the Vs minus of V naught, and switch is off, then minus of V naught appears here. Same thing here. IL, if switch is on, then voltage will be increased, current will be increased. After that, if switch is off, then this will be decreased. So it increases. Average of this one, inductor current is the I naught. IL is equal to I naught. And here, IT, it means terminal current of input in or input current. Input current when switch is on, then input current is flow. But when switch is off, the input current will be 0. So you can say here, if a input current is flow, when switch is on, then this current will be flow in input. This will, after that, this will be 0. Same thing. Then you can say for the in a steady state, you can say this one current is flow at the input side. Then this current same as the IL current, because of this when switch is on, the same current flow like IL in input side. When switch is off, then it will be 0. And you can say is the IT average of this one, the same as IL is current flow when switch is on. It means a duty cycle of this one only. When if this current is flow when switch is off, then this will be multiplied by 1 minus d time, because IL into dt divided by dt usually the duty time is the total time period. Look, LC loud, it will be IL into t, and IL is same as the I naught or the buck converter. Then you can say is the R naught is equal to V naught divided by of I naught. V naught is equal to d Vt. This one I naught is equal to It divided by of d. Vt by It is equal to RT into d square. Then RT is equal to R naught divided by d square. For the buck converter, at d is equal to 0, 1 by RT is equal to infinity. It will be 0, I think. 1 by RT, because of this one, 1 by RT is equal to d square divided by f R naught. If d is equal to 0, the 1 by RT is equal to 0. It means this one is a open circuit. And at d is equal to 1, then 1 by RT is equal to 1 by f R naught. It means at open circuit, you know about the open circuit line, Vt, It. Cell line is the maximum power point line, 1 by RT. Vm, this one maximum power. This is a load line. If D is equal to 0, then this will be open circuit. It means D is equal to 0 here. One by RT is equal to 0, and at D is equal to 1. This is be 1 by RT equal to Y naught. At D is equal to 1, 1 by RT is equal to 1 by of R naught. For the buck converter, the operating area is this one only. If the maximum line is not here, means if the maximum line is here, maximum power point line is here, then you can't be get the maximum power from the solar, because the range of this one is the only this. For boost converter, this one is here to this one is here to here only. For buck converter, it will not a full, this will here to here only. Last one is the buck boost converter. Buck boost converter is this one. Then Vt, this one will be It, so IL, I naught plus minus of V naught, C, IC, sorry, you know about the output voltage of buck boost converter is dVt divided by F1 minus D, and same thing for It, IL will be, if we take an average as an average of IL, the IL is equal to, this one will be current of I naught because of average IC is 0, IC average current of capacitor is 0. At average, this one will be the It, IL is equal to It plus of I naught. And you know about when switch is on, and switch is on, this current will flow, and when switch is off, then this current is flow like that. It means you can say is It average, I average of input current is the D when switch is off, on, into average of the inductor current, and inductor current average value is same as the It plus I naught. That's why you can retain as the this one is It plus of I naught. Then you can get this one It current from here, Y naught into D divided by F 1 minus D. This will be 1 by this one DIT, transfer to the left side, then you find the IT. V output R naught is equal to V output divided by F I output. Yes, this one D Vt divided by F 1 minus D into I naught is equal to 1 minus D into It divided by F of D. Then Vt and It is D square divided by 1 minus D whole square into Vt It is equal to RT. You can get the RT here. R naught into 1 minus d by f d whole square, or the buck boost converter. Then whole 1 by RT is equal to same thing, 1 by R naught into d divided by f 1 minus d whole square. At d is equal to 0, 1 by RT is equal to 0. At d is equal to 1, 1 by f RT is equal to infinite. And Vt, this one will be It. Same thing, draw characteristic of the solar system. This is the load line for the maximum power, 1 by RT, Vm, this is maximum power, this one is the max Im. The load line at d is equal to 0, d is equal to 0, it will be 0, it means open circuit. Here d is equal to 0, 1 by RT is equal to 0, open circuit, and when d is equal to 1, d is equal to 1, 1 by RT, infinite means short circuit, this line. And buck boost converter, you can see here, the whole region will become under buck boost converter from 0 to 1, and anywhere if power point is there, then you can get the maximum power from the PV panel by using a buck boost converter, because the load line is vary from open circuit voltage to the short circuit current. All of the region is covered from the buck boost converter. That's why the best converter, DC converter for the maximum power point taking, is the buck boost converter. Cascaded buck converter is same thing. Buck converter converter connected in back to back series only. The same buck converter have a region is different, not full region, but buck boost converter have a whole region of the PV system. Okay, next question. Why input capacity is mandatory at the PV panel output of the maximum power point tracking with the buck converter? You know about buck converter? Buck converter in input side is switches is connected. The switches is connected, that's why the current will be discontinuous when switch is on. The current will flow in input side, when switch is off, then current will not flow in input side. That's why to maintain the continuous current of the PV panel, to protect them, then you can apply a, you can connect a capacitor at the input side. This is the circuit diagram of buck converter. Sorry. This switch is connected in the input side. That's why when switch is on, then current will flow. Switch is off, then current will not flow. That's why a capacitor is should connect at the input side to maintain this current will be continuous. When switch is on, this will be the current flow. When switch is off, this current flow through the capacitor. When switch is on, that both current flow from there. That's why this will be in continuous connection mode. The option is the input voltage of the buck converter is discontinuous. No. Output voltage is maintained. Input voltage, sorry. The input current of the buck converter is discontinuous. Yes, this will be correct. The inductor current of the buck converter is continuous. The inductor current, yes, it's continuous conduction mode, this will be continuous. Then the diode current of the buck converter is discontinuous. The diode current not affected this one. Sorry, this will also not affected the input source capacitor. Then it is only for the input current is discontinuous. That's why you apply the capacitor to input side. A 45 watt DC-DC converter shown below. This is the boost converter. Well, shown below as a following parameters, switch Q is saturation voltage of 0.2 volt and the forward voltage of the diode is 0.7 volt. When switch is on, then this is 0.2 volt is the saturation voltage, and then the forward voltage of drop of the diode is 0.7 volt. When switch is diode is on, then 0.7 volt the voltage drop of the diode. And what is the input current in amperes of the converter for a duty cycle of the 0.4 under continuous conduction mode? Okay, this one is the boost converter. Boost converter, first of all find the output voltage. What is the output voltage? After that you can find the output current through the relation of the output current in the input current. I have written here switch is on. Then what is the circuit of this one? This is a Vs. It has the input voltage. Vs supply voltage inductor. This switch is on. It means this is short circuit, but with a voltage source of 0.2 volt because of the voltage drop of this one. And this is in reverse wires. The same thing. This was supply the current to the load at that time. The switch is on. The switch is on. This is the circuit diagram. This is in reverse wires. Capacitor, output resistance, or not. This one output voltage. I written this one is the VQ voltage drop. It's an L. There is VL. This one is VS. And then apply the apply the KVL. Then you get the VL inductor voltage is the VS minus of VQ. And IC in capacitor current is minus of I naught. So to apply for the on off condition, and switch is off, then this will be the off, no more current flow from here. This will be the forward bias. This will be forward bias, but it will not be short circuit. It will be 0.7 voltage source or 7 volt. This is given as the forward voltage drop of the diode. Then this circuit looks like this one is open circuit, plus minus 0.7 I written as VD. IL, this one is VL, VS. Same thing, apply a VL with the KVL, then get the VL. Inductor voltage is Vs minus of Vd minus of V naught. IC, same current IL flow here, that's why IL minus of I naught is the IC. Then apply a volt second by length equation, apply on the inductor. It means D into VL on time to VL plus of off time into VL, wherever total time is equal to 0, average voltage of the inductor is 0. D on time voltage Vs minus of VQ, off time voltage is 1 minus D, off time voltage is Vs minus of Vd minus of V output is equal to 0. This will be dVs minus of dVq plus of Vs minus of Vd minus of V naught minus of dVs plus of dVd plus of dV naught is equal to 0. dVs will be cancelled out, remaining is there. V naught is here and here, you can get the minus of V naught common, then we get the 1 minus d plus Vs is here, Vq is not there, only dVq, Vd is there, then you can minus of 1 minus d common. If you take common of Vd, then you will get this one. And for the output voltage Vs minus of dVq minus of 1 minus d into Vd divided by 1 minus d. This is the output voltage of this one, this converter. It means this one is the switch to the switch output switch on saturation voltage. This one is diode on conduct voltage. If this will be 0, then same at V output is the Vs divided by 1 minus d is the boost converter output voltage expression. But here the switching loss is there, that's why. This one the volt second, then find the current second balance. Current second balance equation dt into Ic plus of 1 minus d t into Ic is equal to 0. D into minus of I naught plus 1 minus d into IL minus of I naught is equal to 0 minus of d I naught plus of 1 minus d IL minus of I naught minus plus of I naught d I naught is equal to 0. D I naught will be cancelled out, then you can get the IL is equal to I naught divided by f 1 minus d, or I naught is equal to IL into 1 minus d. All of thing in average value, that's why I have written in the calculator. All of thing IL is equal to I naught divided by f 1 minus d. I naught is equal to IL into 1 minus d. You know about the boost converter, the same thing. IL inductor current is same as the input current. Input current is asking the question, I think. So what is the input current? Input current, it means same as the inductor current. Here IL is same as the IN is output current divided by f 1 minus d. Duty cycle is given 0.4 and 45 watt is given as the power. If any power is given for the buck converter or any system, any electrical system, then it means the output power. If the rating is given, it means that rating is the output rating only, not the input rating. It means the 45 watt DC-DC converter is 45 watt is the output voltage, output power of the converter. This means P out is equal to 45 watt. R naught is given as 10 ohm. Then what is the I naught? I naught is equal to P output, no, about the I naught square into R. Then I naught is equal to P naught by R under root. You can get the output current. Root of 45 divided by F 10. If you solve this one, you can get the output current is 3.535. ampere. If output current is there, then duty cycle also given as the point 4. Then you can get the input current 3.535 divided by f 1 minus 0.4. Sorry. I think this one is not input current. 4 4.5 root of 4.5 is a 2.121. Sorry, 2.121 ampere. 2.121 ampere divided by a point of 6, because of 1 minus d is equal to 0.4. Then you can get the input current is 3.535 ampere. This one is the input current. Okay. Same thing for the next question is given. What is the load resistance in ohms seen by the PV panel? In question number 3. For the same question, it will ask about the load resistance in ohms seen by the PV panel. It means the input resistance of the converter. Input resistance or in V in divided by of I in. I have calculated I in. Then first of all find the V in. We will also calculate the output expression as the Vs minus of 1 minus d into Q Vq minus of d into Vd divided by of 1 minus d. Sorry, I switch current is as input side, that's why switch is on, and this one will be the Vq, and switch is off, that time diode current is flow, that's why minus of Vd here. Then you find the Vs or V in, same thing. V in is 1 minus d into V naught plus of 1 minus d into Vd plus of d into Vq. V output, first of all find the V output. V output is equal to I naught into R naught or V square by R. You can say calculate this by this one also. I naught is calculated here 2.121 into multiply of 10 resistance, it will be 21.21 volt. 1 minus d is equal to 0.4, it means this will be 0.6 into 21.21 plus of 0.6 into Vd is given 0.7 plus d is 0.04 into Vq is 0.2. Calculate this, you can get the input voltage. (13.226). 6 is the input voltage. Then what is the input resistance? It's the V in divided by I in. 13.226 divided up 3.535, I think 3535 divided by 3.535 3.74. Okay. Next question, what is the efficiency of the converter? Discuss in the question 3. Same question, what is the efficiency? You know about the efficiency, the output power divided by of input power. Output power is V output, I output. Input power V in into I in. Output power already given is the 45. Input voltage is 13.226. Input current is 3.535. If you calculate this one, we will get the 96.25% of efficiency of this converter. Okay. Then what is the input impedance seen by an ideal boost converter? Same thing I will draw already in this one. Or not is the output resistance of the converter and D is the duty cycle. This one you can by the simply same thing, A option correct. For the ideal boost converter is P in is equal to P output V in into I in, V output, I output, V in is equal by R in divided by R in, and V output is square divided by R output. V output is equal to, for the boost converter, V in divided by of 1 minus D, put here V in divided by R in, V naught is equal to V in square divided by R output into 1 minus D square. Will cancel out. R in is equal to R naught into 1 minus of D square. This one, A option correct. Which of the following converter has a continuous input current? Buck converter, boost converter, inverted output buck boost converter, and cascaded buck converter. Input current. I already draw the circuit. That's why I will see you. This is the boost converter. When switch is on, then current will be flow like that. And switch is off, then current flow like that. It means input current will be continuous in boost converter. Looks once again, when switch is on, this one, then current will flow like that. When switch is off, then current flow like that. It will at that same time, then both time, the input current will be continuous. This is the boost converter. Same thing for buck converter, input current will be discontinuous. Already so here, if switch is off, then current will be 0 in input side. For buck boost converter, same thing, buck converter input side, boost converter output side, the same thing. You can get is the input is the discontinuous current here. When switch is off, then current will be 0. When switch is on, the current will be flow. That's why discontinuous current. The continuous current has the continuous current of input side is only boost converter. Buck converter and buck boost converter both are the discontinuous current at input side. Next question, what is the relation between input voltage V in and output voltage V output in buck converter when the load is open circuited? A, V output is equal to V in. Yes, correct. This one open circuit C L, and say this one output voltage VL, VC. VC is same as the output voltage. This will be VS or V in. and switch is on. If you switch is on, this one current flow like that, the circuit will be VDC, DC voltage connected to the LC circuit. A DC voltage connected to the DC source is connected to the LC circuit. Anyone know about the current expression, current nature? Because output voltage is a discontinuous. Output voltage zero, output load is infinity, means open circuit. Then this will be connected to the LC circuit. For this one, if the switch is on, if you do the switch is on here, then current flow like that. At that point, capacitor will charge some point. If the capacitor is charged from some point to the V in, because of switch is on, the capacitor will charge, but the capacitor will not discharge anywhere. It will be charged only. If on this one is charge is the same as V in, charge voltage is same as the V in voltage, at that point conduction will be off. Any conduction not happen, or any current will be zero. If you on the switches, then capacitor at that time capacitor will charge, and capacitor will charge at that point like a V in voltage, some point of V in voltage. At that point the capacitor will be behave like a open circuit. It will not charge. If this will not charge, that means the current will be zero. At that point, it means you can say that Vc is equal to V in. At that point of Vc is equal to V in, the output voltage is same as the V in, Vc. At that point, the current will be zero. Current will not flow anywhere. In steady state, you can say the output voltage is same as the input voltage. And if you want to find the expression of the current in DC system and DC source with LC circuit, then you will get the sinusoidal nature. I will not draw the everything. I give you a hint how estimate the current. You can say this one IL by KVL V in is equal to VL plus a VC, same thing. V in this is L didt. VC you know about the 1 by C integration of IL into dt. If you want to express in Laplace, then you will find V in divided by of S. This will be Ls 1 I by of Cs, LL2S into IS IL plus 1 by of Cs to IL. So I, this one is yes, Laplace domain, this one is yes, this will be IL. Take LCM denominator, and will be the V in is equal to L into S square you can say this one is LC also, LCS square, sorry, 10 like N to 1 by of C. SS will be cancelled out from input side. IL is equal to V in divided by L into S square plus 1 by FC. Take L as common, then we will get the S square divided by 1 by F LC. Okay, everyone, you know about the Laplace, na? Simply convert into Laplace. After that, find the input current, the current expression. This S square plus 1 by LC you can retain as 1 divided by F S square plus 1 by root of LC whole square. You know about the sin omega t, sin AT Laplace A divided by of S square plus A square. Same thing here is A is equal to 1 by root of LC. Then multiply of root of LC in denominator and numerator. One by root of LC divided by of S square plus 1 by root of LC into 1 by root of LC. Sorry, denominator divide by this one. This one multiplication. For division, we should apply here 1 by root of LC. This whole thing is the sinusoidal. If this one root of LC, root of L, root of L, we can say the root of L will be cancelled out. Then B in into C will be goes to the numerator C by L into this one will be sin 1 root of LC into T. You can say is IL is V in, I written as directly IP. This one will be sin omega t. So if you convert into T, that this will be in T time domain. Where IP is equal to V in into root of C by L and omega is equal to 1 by root of LC. It is mean the current will be sinusoidal. Here I written I T is equal to IP sin omega t. Then what is the inductor voltage? VL. VL is equal to L di of dt. Indicate this one. Then you can get as Vs cos omega t. V in cos omega t. All of cancel out. Please do by oneself. And VC. VC is equal to Vs. V in minus of VL. VL is Vs. Then V in common. Then we will get the 1 minus cos omega t. On, this one off, left this one. So for the off, oh, sorry. The switch is on, current IL, VL and VC. VC is same as the output voltage. VC is connected here. IL glows like that at a sinusoidal, but till the VC will be at Vs. Till this one is the Vs. If this one is equal to Vs, Vc equal to Vs, then circuit will be current will be 0. If a current will be 0, then VL inductor voltage also 0, like that in sinusoidal cosine wave. This will go into 0, but this will be 0. When this one will be 0, but current will be fully 0 when capacitor reach the Vs value. That's why Vc is equal to Vs when load is not connected. Because of this, you can say also the flux balance and the charge balance phenomena is not present here. That's why conductor and capacitor will not work because of the inductor goes to saturation mode and capacitor is fully charged, then it will open the whole circuit. That's why the voltage input voltage is output voltage is same as the input voltage. But when a when a DC supply connected to the LC circuit, then current will be in sinusoidal nature and inductor current will be in cosine nature, and capacitor voltage is 1 minus cos omega kind sine 1 minus cos in nature. Next question, which of the following is isolated converter? Buck converter is non-isolated, flyweight converter is isolated, boost converter is non-isolated, forward converter will be isolated. Then yeah, this will be not, this will be buck boost converter is not isolated, half bridge converter isolated, push pull isolated, full bridge also isolated. D option is correct. Sorry. A 250-watt buck converter is designed for a PV panel which has the following parameters. What is the duty ratio factor in the range of 0 to 1 required for maximum power point tracking? If the converter is connected to the load or not is 0.5 ohm. Consider the ideal condition and assuming continuous conduction mode of operation. Okay, or not is given 0.5 ohm. Output power is given 250 watt. This is the rated power. You can operate maximum output power up to 250 watt. I designed for this one. P maximum, you know about the P max for the solar is VMP, Vm into Im, voltage at maximum power point and current at maximum power point. It will be given as a 250 watt max peak power. For the ideal condition, you know, output power is same as the input power. This is the V output square of R naught. This is the V in square of R in. For the buck converter, this is design buck converter. V output is equal to dV in, then d square into V in square divided by R naught is equal to V in square divided by R in. V in will be cancelled out. R in is asking about the duty cycle. Duty cycle is equal to root of R naught divided by of R in. R in decided by the maximum voltage, maximum power. Because of the maximum power, we are asking about the maximum power. Then the R in at maximum power point, the maximum voltage and maximum current divided by maximum current. Current at a maximum power point. Then Vm is given in data sheet is 29.57 and the maximum current IMP is given as 7.63. There will be 29.52 and this will be given as a 7.63. Then calculate this one. We will get the answer of this one. I think 3.8699 approx 3.87 ohm. Then duty cycle D will be calculated from here. R naught is given 0.5 ohm. This will be a 3.87 R in, and calculate this one 0.5 divided of 3.87 and taking the root of this one is equal to 0.359. The duty cycle where you can operate to get the maximum power of solar. So is asking about what is the duty cycle, duty ratio factor. Okay. Next one is the data sheet specification of the solar panel is given below. What should be the load resistance connected so that the load drawn maximum power from the solar panel? Simple, you can say that RS is equal to RL. The RS is on to maximum power same as the VMP divided by of IMP 35.4 divided by 4.94. Simply you can say this one 7.16 ohm. First option, because it is not given as the like any converter is connected between them. It is given only what load we can connect to get the maximum power point. It means you should connect the load resistance same as the source resistance. The source resistance is the at maximum power point is the maximum voltage divided by voltage at the maximum power point and current at the maximum power point. Then divide to this one and find the RS, source resistance. Source resistance same as the RL. RL is same as the RS to get the maximum power. That's why. Next one is given a resistance of 10 ohm needs to be connected to a PV panel. Panel specification I think same as the above question. VOC, ISC, VMP and IMP. In order to extract the maximum power, a boost converter is connected in between load resistance and the panel. Then the duty ratio at which the boost converter should operate in order to extract the maximum power. Previous question is the converter is not connected. Here is a converter is connected like a boost converter. Then you ask about the duty cycle because the load is fixed. There is not load fixed. They are asking about the load resistance, but here the load resistance is fixed by 10 ohm only. Then what is the duty ratio to get the maximum power point? By the duty ratio, you can change the load resistance to match the source resistance. What is the R in requirement of resistance? R in same and you can calculate Vm divided by IM In previous question same is 0.16 ohm, or not also given like a 10 ohm. For the boost converter I will already draw the resistance RT as same as R output into 1 minus of D square. That's why you can calculate the 1 minus D R in divided by of R naught. R in is equal to 7.1610, it means 0.716. Then 1 minus D is equal to root of this one. Root of this one is 0.846. Then D is equal to 1 minus 0.846. It is equal to 0.154, the duty cycle for this question. Next is given the IV curve. Current and voltage curve of the PV panel is given with the maximum power point. If the converter shown below, this is the converter with the switches S1 and S2 at through 1 for the duration of DTS and at through 2 for duration of 1 minus DTS is used for the impedance matching, then the operating region will be sector 1, sector 2. From here you can say this sector 1 for the boost converter, sector 2 for the buck converter, and buck boost converter is the whole region for the buck boost converter. Then first of all find the input resistance. It means IPP and VPP divided by VPP. If you find the input resistance, then it will get the sector where it will be work. What is operating region? From this equation, if a switch is on at position 1, then this is looks like current flow from inductor and the capacitor. Previously, I think you charge it will supply the output resistance. This will be output current. This will IC R naught plus minus of V naught, VPB, IPB. Written as Q is on and switch is on. Inductor will connect directly like that, and other thing capacitor will connect through the resistance or not, as soon as of V naught, I naught into IC. This will be VPB, IPB. Then what is the VL? VL is equal to VPB. Apply KVL here, only this one connected. When switch is off, but off it means the at position 2. In this equation, if the switch is position at 2, the input side will be discontinue, and this current will flow like that. It means inductor supplied power to the load. This is not a Q1. Switch as position at 1, switches at 2. Whole of thing, this one connect like that. I exclude that of thing. So VL, IC, I naught, R naught, V naught. Then what is the VL? VL is equal to minus of V naught. Then apply the Bolt second balance equation. Right in here, by Bolt second balance equation, average of inductor voltage 0. So D into VL, dt into VL plus 1 minus D T into VL divided by FT is equal to 0. D T cancel out. VL is VT. When switch is on, what position 1, and so at position 2, this will be a minus of V naught. Calculate this one, you get the D VT divided by F 1 minus T. For power balancing, because of the not given any resistance and any other parameters, then you can balance the power. Input power is equal to output power. Losses is not given. Then this will be VT square divided by F RT. V output square divided by R naught. V output is D divided by F 1 minus D square into 1 by F R naught on VT. VT will cancel out. RT is equal to R naught into 1 minus D divided by FD whole square. I think you can see in this way it looks like a booster, buck boost converter. At D is equal to 0, if D is equal to 0, this RT will be infinite. It means open circuit. Then 1 by RT is equal to 0. At D is equal to 1, RT is 0, 1 by RT is infinite. This will be open circuit, this will be short circuit. VT, this will be IT. So maximum power line. This is where the open side D is equal to 1, D is equal to 0. This line for D is equal to 1, and whole region will be in operation. This is given, I think, sector 1, this one sector 2, and sector 1 and 2 both comes into the operating region. And what the operating region? Both, I think sector 1 and sector 2. This will looks like a boost converter, buck boost converter. Next question given, for the systems on below, if the VPV and IPV is greater than the RL, then the tracking maximum power the interfacing DC converter should be. Is given VPV divided by of IPV is greater than RL. RL is same as the, you can say like V output divided by of I output. It means VPV divided by of IPV greater than V output divided by of I output. For the ideal condition, you can say that VPV IPV is equal to V output I output. And what is the output here? I output here. VPV IPV divided by a V output. VPV divided by F from here. IPV B output same as I output is VPV into IPV. Do we have V output? IPV cancel out, V output is going to there. Then you can say that VPV square should be greater than V output square. It is VPV is should be greater than it is greater than the V output. So when the input voltage is greater than output voltage, so means buck converter or buck boost converter. You can say this buck converter and buck boost converter. You can step down the voltage from this. Option is given buck boost or buck. Yeah, this one. Yeah, boost one, not one. Yeah, this one buck, but buck and buck boost and buck are also given. That's why option third. If the following circuit is used to test the maximum power point algorithm, then at maximum power point the voltage at the load will be. What is the voltage at the load? Question number 15 is given like you know the maximum power. This will if you take a current as I, then what is the power? Load power is I square into RL. I take it like RL or load. I is Vs divided by resistance. Vs divided by of Rs plus of RL square of this one into RL. Then a PA output load power is equal to Vs square into 1 by Rs plus RL square output of RL. To get the maximum power, integrate this one, differentiate this one with respect to the load resistance. This will be Vs is constant, then this will be the denominator and differentiation of numerator is 1 minus of numerator, differentiation of denominator is 2 into Rs plus RL, and differentiation of Rs plus RL is 1. Rs is 0, RL is 1. Rs plus RL whole square, it is equal to 0 for the maximum. To check the maximum, 0 it means Rs plus RL whole square minus of 2 RL into Rs minus of 2 RL square is equal to 0. It will go to the right side is with 0. Rs square plus RL square plus 2 Rs RL minus of 2 RL into Rs minus of 2 RL square is equal to 0. This will be cancelled out. It will be Rs square minus of RL square is equal to 0. That's why RL is equal to Rs. It means to get the maximum power, RL should be equal to the Rs. RL should be equal to the Rs. It means this will be the Rs only. Rs. Then what will be the voltage of this one? By voltage divider rules, VL is equal to total voltage Vs into that resistance divided by total resistance. Vs divided by up to 0.5 Vs. In this one. Next question is given like in order to transfer the maximum power to the load, the value of Rs should be. Anyone can guess this one? For the maximum power, what value of Rs? It will 0 are equal to the load resistance, or equal to the half of the load resistance, or quarter of the load resistance. Anyone can guess this one? Looks, see in here. Every time is asking about the load resistance, not asking about the source resistance. Maximum power point theorem also says that about the load resistance. If the load resistance is varied, then you can get the maximum power by matching the load resistance to the source resistance. It means the load resistance should be equal to the source resistance. If the load resistance is varied, it means RL is equal to of RS. But when the source resistance is asking about the source resistance, then should be 0, must be 0. Only must be 0. Source resistance must be 0. If the source resistance is 0, then power losses is 0. The power losses is 0. Then all of the power is delivered to the load. That's why it will be 0 ohm only. It is not equal to the RL load. It is asking about the source resistance, not asking about the load resistance. Source resistance will be minimum as possible, or must be 0. At 0 condition, the all of the power transfer to the load. None of the power is loss. That's why this is the 0. Next question is, when a buck converter is operated with the following specification: input voltage 36 volt, output voltage 9 volt. If the average value of current through the diode is 0.375 ampere, then the input resistance of the converter. This is the buck converter. Right, and is SQ, so diode, Veblen diode. This, I will take a class. Keep there. VL is the capacitor. So output resistance, so output voltage, output current. All of you know about the expression of output voltage for buck converter is dps. Then first of all calculate the duty cycle. D is V output divided by F Vs. V output is given as 9 volt, Vs is given as the 36 volt. This will be 0.25. Okay. And RS, you know, buck converter. Confuse this. Should apply the power equal. Vs is equal to V naught I naught. This will be the Vs square divided by FRS. V output divided by the RA output. V output is equal to, this is the R Vd square of Vs square. Vs will be cancelled out. RS is equal to R naught divided by F D square. R naught is equal to, R naught will be given, I think this is not given, R naught. Then first of all calculate the R naught value. Okay. something is given, like is it given as the current through the diode resistance, sorry, diode. This current is given is 0.375 amperes. This is the on condition, this is an off condition, this will be on condition. Inductor voltage, when switch is on, then Vs minus of V naught appears. For the KVL you can see here, this will be a Vs minus of V naught. When switch is off, then all of current flowing through the diode, and the voltage inductor voltage will be minus of V naught output voltage. The same thing, Vs minus V naught. What if the inductor current, when switch is on, then current will be increased from minimum current to the maximum current. Same thing, switch is off, then maximum current to the minimum current, it will flow like that. This will be a IL current, this will be a I minimum, so I maximum. This will be flow in steady state, not transient time. Transient time not so in the graph waveform, it will be steady state current only, charging discharging current. So that's why the minimum current to maximum current will show like a continuous conduction mode of converter. Next is given a diode current ID. Looks here, ID when switch is on, then diode will be in reverse bias. That's why current will be 0. And switch is on, then switch is on, the current will be 0. Diode current will be 0. But when switch is off, then this is the inductor current. Inductor current, same inductor current flow through the diode. You can see here, same inductor current flowing through the diode. And all of the inductor current, this current flowing through the diode. After that, switch is on, this will be 0. Then what is the average current? This is the average current of IL. When switch is on, then this will be 0, then switch is off, then this will be 0 there, and 1 minus d into time. Diode current is present. Then ID is IL, average current I take in the IL into 1 minus of dt. We have total time period t is equal to IL into 1 minus d is the diode current. And IL is same as the I naught for the buck converter. Because of the average current of the capacitor will be 0. This is written as the I naught into 1 minus of d. ID is given, duty cycle also I will calculate it. Then what is the I naught? I naught will be ID divided by of 1 minus of d. ID is given in the question like 0.375, and duty cycle is given 1 minus 0. I have calculated 0.25. Then this will be a 0.5 ampere. I naught. Then what is the R naught? R naught is equal to V naught divided by of I naught. V naught is given as 9 volt in the question. I naught I have calculated like a 5 ohm, 0.5 ampere. This will be the 18 ohm. R naught calculated, then calculate the source resistance also. Source resistance is the 18 divided by of d square. D square is equal to 0.25 square. This will be a 288 ohm. Okay. This one. Next question, same thing, referring to the question number 17, that means the previous question, the duty cycle of the operation of the converter. Same thing I have calculated, 0.25 by the input voltage, output voltage. V in given as 36, V output given as 9 volt. Then duty cycle is V output divided by of V in, 0.25. Next question, referring to the question number 17, average value of inductor current. IL is same as the I naught. For the buck converter, I have usually calculated already 0.5 ampere. Next, when referring to question number 17, there is the switching frequency of the converter is 100 kilohertz, and the value of inductors used is 6.25 millihenry. Then the peak to peak inductor current to ripple will be each. To find the peak to peak ripple current of inductor, peak to peak inductor current or ripple current, to find the any converter like buck converter, boost converter or buck boost converter, first of all find the on duty cycle voltage of the inductor. Like when switch is on, then what is the voltage? VL is same as Vs minus of V naught for the buck converter. This is for the question number 17. Sorry, this one is the given as the buck converter, because this buck converter is in by buck converter switch is on, then VL will be Vs minus of V naught by the KVL. In for the boost converter, it will be a plus Vs only. For boost converter, only Vs. Then first of all, to calculate the ripple current, a peak to peak inductor current, then find the on voltage like a VL is equal to Vs minus V naught. You can calculate it by the off voltage also. Then VL is equal to L DIL by dt. This one is a Vs minus of V naught. Then DIL by dt is equal to Vs minus of V naught divided by of L. Then DIL is equal to Vs minus of V naught divided by of L into dt. To integrate this one, IL for find the inductor current, then take a limit for the inductor current flowing from minimum to maximum current, I minimum to IL maximum. Then integrate this one, IL minimum to IL maximum. Look here, this one IL minimum to current flow from IL minimum to IL maximum. Then what is the time from reaching the I minimum to I maximum? This will be on time. On time, this will it means dt time. Dt is the on time or minus dt in the off time, and this will be the current reached from I minimum to I maximum to I maximum. This will be in the time of the dt's only. It means if you take like this one is 0, then this one will be a dt time. Then integrate that in time domain, integrate from 0 to dt, and in the current domain integrate from IL minimum to IL maximum. This will integrate 0 to dt time. Then this will be a 1 only DL, then 1 will be IL maximum upper limit to the lower limit minus IF minimum is equal to, this will be all of the constant Vs, V naught and L. That's why a Vs minus of V naught, this will divide by L of constant, only 1 is there, it means 1 is the dt. IL maximum minus IL minimum is the delta IL. Ripple current minimum to maximum, Vs minus of V naught, dt is the time period, it means 1 by t is the duty, 1 by t is the frequency. Then this will be Vs minus of V naught divided by f L into f into d. All of thin is given. Vs is 36, this one is 9, L is given like 6.75 millihenry, it means 10 to the power minus 3. F is given 100 kilohertz and 10 to the power 3. Duty cycle is I have calculated 0.25. Then this will be a 1 divided by 100. This is 10 to the power minus 3, 10 to the power plus 3 cancel out. If this will calculate this one third 26 into 2.2 by 6.2 6.75, that's value 6.75 will be cancelled out. It will be 1 divided by of 100. You can say this one is 1 10 into 10 to power minus 3, because of the answer is given in milliampere, that's why 10 milliampere is the ripple current. This one. Okay, okay everyone, I am stopping here.